There's one more thing that we can calculate with a dipole, and that is the potential energy of the dipole. So we have the dipole aligned like this, and we want to find its potential energy, what potential energy it has. So to find the potential energy, we always start with this equation. The change of potential energy is equal to negative of the work done by the conservative force. In this case, the conservative force is the electrostatic force, right? Okay, let's plug in the formula for work done by a torque. In this case, the work is done by a torque. So it's going to be minus tau d theta. So that is the work done by the conservative force. It's tau d theta. And so the delta U means U final minus U initial. And I use this this convention that if I don't put a subscript, it means the final. And if I put a subscript 0, that means initial. Sometimes books will do U sub I minus U sub F. I don't like that. I just like to do no subscript means final, and 0 subscript means initial. So that's my delta U. And that is equal to minus the torque. I can put in the formula for the torque. That's minus PE sine theta d theta. So all I did was just put in the formula for the torque that we just derived. And this goes from theta initial to theta final. That makes sense? So the overall minus sign that I have, that comes from the formula. Delta U is equal to minus WC. And based on the sign convention that we are working, our torque was negative. So that's why I have a minus sign in here. So I simply put the formula for the torque over here, right? Okay, so now we have to do one line of algebra over here to work this out. So the two minuses make a plus, right? So I can, and P and E are constant, so I can pull them both out. P is constant because it's a property of the dipole, and E is constant because we assumed that we are in a uniform electric field. So that's why both of these are constant, and I can just pull them out of the integral. And I just have to integrate over sine theta from theta initial to theta final d theta, and that is U final minus U initial. All right, now the integral of sine theta, as you know, is negative cosine theta. So I get minus PE cosine theta, and then I have to just plug in the limits theta final and theta initial. That makes sense? All right, and so we are almost done. So U final minus U initial is equal to minus PE cosine theta minus cosine theta initial, right? All right, our goal is to just find U as a function of theta. That's what we want to find, right? That's fairly obvious from here now. If I write it like this, U minus U initial is equal to minus PE cosine theta. And the second term, I'm just going to write like this, minus PE cosine theta 0. Right? So I just wrote it like that. Now you can see that U must be minus PE cosine theta, and U initial must be minus PE cosine theta naught, right? Which tells you that the general expression for potential energy is minus PE cosine theta. And that's why U initial was minus PE cosine theta naught. And this is what I was after. So U is equal to the potential energy of the dipole is minus PE cosine theta. Remember that P is a vector and E is also a vector. So PE cosine theta, what does that remind you of from physics 1? The dot product, exactly. So another way of writing this is U is equal to minus P dot E. The dot product always gives you a scalar. So you can see that the potential energy of the dipole is the dot product of the dipole moment and the electric field, right? And the torque on the dipole is the cross product of the dipole moment and the electric field. That makes sense? All right, so these formulas will come up later on, and you'll see very similar formulas show up for magnetism as well.